Hi, welcome to this video where I'm going to go through section 9.3, graphing reciprocal functions. So a reciprocal function is defined by the parent function f of x equals 1 over x. So your variable is in the denominator of that function. It's not linear. It's going to actually make a curve with the variable being down there. So we'll just go through a couple examples of these, starting with some story problems, and then just take a look at some graphs and then transformations. So first off, a school is looking to have a prom at Miller Park. To hold the event, there's a $3,000 rental fee. So that's going to be divided between everybody that goes, plus the $40 per meal. Before they make a decision, they want to know the approximate cost per person. So we want to define variables and write a function that represents cost per person. First of all, talking about why this is not linear, I see that it says $40 per meal. So that would be like y equals 40x. But we're not charging each person $3,000. So keep in mind that this fee is going to be split up between everybody, so we're not going to have a linear equation here. So the first thing that I am going to do then is defining those variables. X is going to be the number of people, okay, which is already different than this one. And then f of x, instead of saying y, I'll just say f of x, and that's going to represent the cost per person. So what'll happen then is we're going to write a function that's just going to input the number of people that are there. So it's 100, 200, 300, whatever it is. And then our output values are going to represent the cost per person. So f of x equals, and again, we're going to take that $3,000 and we're going to break it up between everybody that's going there. So I'm dividing it by x number of people plus, again, remember, this is for cost per person. It's $40. So that is my basic function here, where again, the variable is on the denominator. That makes it not linear, it makes it not exponential, quadratic. This is called a reciprocal function. So as far as graphing this goes, I just made a quick table of values here. And this is the one that comes right from the key. What you'll see is I just picked values starting as low as 50 people attending all the way up to 500 people. And the cost per person is drastically decreasing. It looks like it would be exponential at first, but again, keep in mind that from the equation, the variable, your x value, is not in the exponent spot. It is in the denominator. And that's what makes it a reciprocal function and not exponential. So you'll notice that the biggest drop is right away at the beginning, and then it keeps dropping more and more. This curve is just going to keep approaching the x-axis, or the y-axis. Down here, it's going to get closer and closer to a value of 40, but it's never going to reach that. So we're watching these values drop, drop, drop. Now, if you were to actually put in a value of like 100,000 for x, you would still see a y value that is not 40. It would be 40 point something, because again, this is going to get closer and closer. And if you think about in context of the problem, why that is, you're always going to be paying that $40 per meal, but you're also splitting up a fraction of that $3,000. So like I said, even if 100,000 people came, 3,000 divided by 100,000 people is still a positive number, and it's a number that's greater than 0. And that implies then that I'd be adding that to my 40, thus never actually reaching 40. So this is going to get closer and closer and never cross. And again, just notice labeling the axes on here, and then that was just the table of values. So what I'm going to do is tweak the problem a little bit and assume that there's 4 members on a committee. Since there's work to be done, they do not have to actually pay to attend the prom. So even though they are not paying, somebody else has to pay for their meals. So it is 4 people, and it's $40 per meal, which is going to add another $160 onto the total. And keep in mind, again, the total for the rental fee is $3,000. So to that, I need to add these 4 more meals, because again, it might seem like they're free, but they're still going to be tacked on somewhere. So that's going to change our function a little bit, because now my numerator is going to become 3,000 plus 160, and I'm still going to be dividing that, but that's not going to be by X number of people, because now I've got these 4 members, so I need to subtract them off of my total. Okay, because they're not paying, so we need to get rid of them from our total attendance, and again, go back to the plus 40 a plate. So just quick explanation again. We're adding the $160 because that is 4 essentially free meals for people, but it's still got to go in my cost, and I'm going to simplify that to 3,160. And then again, if X is the total number of people that are paying, you want to subtract the 4 off that because those members are not. and to that you are adding that $40. So this is our updated function. And what I want you to notice then is if you use that same table of values, and it's on the key, but I would definitely recommend use the same table for your x values, go and take a look at the y's. What ends up happening is the function slightly shifts over and you end up with a vertical asymptote at x equals 4. So in your calculator, if you use that table feature, if you got down to single digits here and all of a sudden you looked at 10 people, 9 people, 8 people, and you kept going all the way down, when you hit 4 for an x value, you'll have an error. And then you can't actually have any value on the other side because then it would be negative, and that those values are not within our domain. So here's where a reciprocal function comes from. Again, this is the parent function, f of x equals 1 over x. I just threw these values in my calculator. Again, if you press second and then window, you can set your table start. If you wanted it to look like mine, I would make your table start -2, and I would make that little change in x 0.5. This way you can get these little values in there. But really, if you're just going to be counting by ones, which you will for the remainder of this, leave your little delta x at 1. And you can make your table start wherever you want. I'll show you in a sec where I would encourage you to put the table, but just keep in mind that with these problems, you're going to have this horizontal asymptote here, and we'll talk about that in the next video. And we're also going to have a vertical asymptote going straight up and down. So this function is going to keep getting closer and closer to those in both directions. So a couple things as far as transformations go, because we are going to do transformations. If I were to shift this x value to the left or right, what's going to end up happening is it's just going to move your vertical asymptote over. So again, if I were to put like x plus 4, you would see this vertical asymptote shift to the left 4 units. If I were to throw a value after the function, that's going to alter your horizontal asymptote. The other kind of transformation that you could see is if I had a dilation, if I changed my numerator to something larger, what it's going to do, I mean, normally what it would do is make our curves a lot steeper. What it's going to do in this case is actually push your curve further away from your asymptotes if you have a larger number out in front. And there's a couple examples that we'll see of those as well. So we'll go through some transformations. Before I do, oh yeah, this is the transformation. So a couple of nice points, again, going back to the parent function, which is what we always did when we came up with our equation. I like to use 2 points and 2 asymptotes. So one of the points I like to do is substitute a value of 1 in. If I substitute 1 in for x, I get 1 for my y value. If I substitute -1 in for x, I will also get -1 for y. So those are the 2 points that I always start with. And I always start with my 2 asymptotes at x equals 0 and at y equals 0. And just like before, we're just going to do our transformation process, where I notice that by my argument of my function in the denominator, I have a +3, and that always did the opposite of what we thought. So I'm going to subtract 3 from my x-coordinates, and that includes the vertical asymptote as well. So since it's an x equals equation, I subtract 3 from that. And then I make the y equation, which is going to have a dilation of 2, and a vertical translation, or I'm sorry, a horizontal translation down 4 units. So my y asymptote is going to be at -4. So that's going to be the horizontal asymptote. I'm going to multiply my dilation of 2 and subtract 4. That's going to give me -2, and then that's going to give me -6. So I plot the 2 points and the 2 asymptotes. And then I'm going to plot my coordinates. So -2, -2 is going to the left 2 and down 2. And again, it's pushed a little bit away because of that dilation up front. And that's going to give me something that looks like this. Oops, I definitely noticed that this is at -3. Oh yeah, that's where I wanted it. Okay. And then the other point was at -4, -6, and that's down here and all the way down here. So again, you're going to see the curves on both sides of your asymptotes. What's going to actually change that then is if I put a negative. So if I had a negative dilation, what you're going to see is your curves go in the other, you can call them quadrants, I guess. They would go in the other quadrants of the actual graph on the other sides of the asymptotes. last thing I guess I would mention is if you're doing a table of values with these, what you always want to look for when you're making a table is to find points that are around this asymptote. So around putting -3 in the middle, pick a couple points on each side if you're using a table of values, because you're always going to see an error wherever that first value is. And again, that's because if I actually substitute -3 into my function, I would end up with 2 divided by 0, and that's undefined. So that's going to automatically give you an error, but you would find values on these 2 points. So again, you can do that in a table of values. But just quickly recapping, because that is it then, that I'm going to go through. Going back to this first equation, keep in mind that this is a reciprocal function. We're going to do rationals in the next section. This is reciprocal functions because your variable is in the denominator. And it's basically, in a story problem sense, is when you're taking a dollar amount or something like this and you're splitting it up between your independent variable. So we went through a couple cases where we had a transformation in the denominator here, which shifted our graph to the right 4 units. And again, that moved that vertical asymptote over to the right 4. We took a look at what the parent function graph looks like, and then just one transformation.